Okay, so today we will be moving into more central and peripheral hemodynamics. Last lecture we started talking about an intro to cardiovascular physiology as well as electrophysiology. So right now, this lecture is going to be focusing on the heart itself and all the mechanisms related to the heart. And then we're going to start into moving into the periphery and going into peripheral hemodynamics after that. Okay, so anytime we talk about the heart and its function as a cardiac pump, anytime we think about its pumping ability, there are three factors to focus on. One, the simplicity of its design. Two, we can look at the wide range of activities it can support. And three, what is its functional capacity? So referring to number one, the simplicity of its design, the heart is pretty basic. We can look at it from two perspectives. We can look at the heart from top to bottom, or a left and right sided pump. So if we looked at it from top to bottom, we're looking at, the atria function and then the ventricles function. And then from left or right side of the, as a pump, like we talked about last lecture, we can talk about it as a high pressure system versus a low pressure system, right? So number two, when we look at the wide range of activities it can support up to a heart rate over 200 cycles per minute, and also below 50 cycles per minute. With its functional capacity, to understand these three factors, we need to understand the relationship between structure and function. And we have to do so at the myocardial cell level. The contractile elements of a myocardial cell are the same as a skeletal muscle cell. So what we talked about last lecture was actin, myosin, cross-bridge cycling, calcium coming in and doing the tropomyosin shift, and all that is going to be the same. And we also have striated sarcomeres in both types. Okay, so when we talk cardiac and skeletal muscle cells, they both show similar length tension relationships. If we took either muscle cell and dropped it on the table, both would go to resting or equilibrium length. I had talked about this when we talked about skeletal muscle cell, so it's similar. So when we stimulate that fiber, it will generate X amount of force. We can manipulate the length of that fiber and alter the force at which it generates, just like we talked about before. So if we stretch the fibers within reason, we can generate more force than what it did at equilibrium length. This is true for myocardial fibers in the walls of our papillary muscles as well. Papillary muscles have the same length tension relationship, just like skeletal muscle does. So the more we stretch our cardiac muscle fibers within limits, within a range, we can generate a larger amount of force. The heart can generate a greater amount of force. Just like when we were talking about skeletal muscle, we can do the same thing when we put it on a slight stretch. Okay, so when we talk about stretching the muscle fibers, we can generate a greater amount of force. But let's talk about overstretch and why this is a problem in the heart. Why is that a problem? Is it because if we overstretch and disengage those cross bridges, that can be detrimental to the heart, right? So we can't not contract with the heart because that affects myocardial mechanisms and living and all that other stuff. So if we overstretched a leg muscle and pull or tore a leg muscle, it's not as detrimental as if we overstretch the heart and tore those muscle fibers apart. So we actually have a built-in response to that and a built-in mechanism, which is called our Frank-Starling mechanism, which is very important. We can stretch these fibers by the amount of fluid we put in the container, which is our heart. So the more fluid in, the myocardial fibers can generate more force because the muscle fibers have been stretched and generates more power. Ultimately, more blood in equals more blood out. So if we enhance venous return back to the heart and we have an increase in the amount of blood that's going into the heart, those muscle fibers in the heart are going to be put on a stretch. The more we put on a stretch, that means we're allowed more blood into the heart. And then that means that heart can generate more force, so more blood in, more blood out. Okay, so let's talk a little bit about the pressure in the heart and the role that plays. In a normal heart, pressure occurs at about 12 millimeters of mercury on the venous side of circulation, and we return fluid to the myocardium. So it's about, when we're returning blood on the venous side, it's about 12 millimeters of mercury. That gives us a cardiac muscle fiber length of about 2.2 micrometers. If we increase the filling pressure to a greater extent, we will stretch those myocardial fibers above that 2.2 micrometers. If we increase the filling pressure to too much of a, we would disengage those cross bridges. But luckily, the heart has that Frank-Starling protective mechanism, so we don't do that. So our protective mechanism is that these fibers only stretch within an operational window. Our window of function is 2.2 to 2.6 micrometers. So we only have about 0.4 micrometers of a fudge factor in there. We will resist stretch at 2.6 micrometers. With skeletal muscle, if we overstretch, the consequences are not nearly as great as if you overstretch these myocardial cells. If we overstretch the myocardial cells, we will disengage the cross bridges and force will drop down to 0. Here we have a serious consequence. Why? Because we're not going to be pumping blood out of the heart then, which is what we need. Skeletal muscle has resistance built in as well, but the consequence is definitely not as great. Okay, so we're still going to be talking about the cardiac and skeletal muscle cells. Cardiac muscle cells operate as a syncytium. What is a syncytium? A true syncytium is, in this setting, is a protoplasm of one cell is free to move back and forth in between cells. That's what a true syncytium is. So cells can freely move in and out of one each other of the protoplasm. So this would be it over here. However, myocardial cells act as a syncytium. They aren't a true syncytium, so their protoplasm doesn't go in and out of the cell like others may be able to do, but they act as one. Right. So they're actually separated along the sarcolemmas on the longitudinal side and separated by intercalated discs on the ends, on the short side. So we see these intercalated discs right here. These are those branches. So why do we say they actually act like a true syncytium? Because the speed of which the electrical signal runs through them is so fast and all at once, it's almost like they act as a true syncytium where one cell can freely flow in and out of the other cell. We want them, like we talked about last lecture, we want these cardiac muscle cells to act as a unit. This is important because we don't want one of the ventricles or a portion of the ventricle to contract before the other. So if we had a portion of our left ventricle contracting well ahead of a portion of the right ventricle or another portion of the left ventricle, we're going to get some confusion there with the amount of blood that's being pumped out, and we won't be as efficient, and we can start to cause problems with that. We want the ventricles to contract as a unit to generate the greatest amount of force possible in order to have adequate stroke volume that can participate in the generation of cardiac output. And we will go over next what stroke volume, cardiac output, and all of that is. But we want those ventricles to act as a unit, to contract as ones with the greatest amount of force to pump the greatest amount of blood out into the body. Okay, so continuing on with the concept of the syncytium, myocardials can act like a syncytium due to plaque-like structures called gap junctions. Gap junctions act like the nodes of Ranvier, like we had talked about with neuromuscular physiology, because myelinated axons have an impact on the speed of conduction as we hop from one node to the other, right? It's in between the cells, and we can increase the speed. So gap junctions almost act like that. Because this gives, so gap junctions actually gives us a resistance-free environment through which the electrical signal can pass or travel through. Like we talked about at a neuromuscular junction, it had to go through that amorphous substance and it had to bind to the appropriate receptor on the postsynaptic side. Here, the electrical signal can go from one cell to the other through these gap-like structures, which are gap junctions. So since this signal goes at such a rapid, fast, and simultaneously, we can say that they act like a syncytium. Right? So our signal has to travel in two directions. One, parallel to the longitudinal axis, which is our long axis, and two, perpendicular to that longitudinal axis. The signal moves much more rapidly parallel to the longitudinal axis due to the gap junctions compared to perpendicular. Okay, so when we talk about the number of mitochondria within the cardiac muscle cells, there are many more in cardiac muscle cells compared to skeletal muscle cells. These are obviously the mitochondria, like we've talked about, are used for oxidative metabolism. The myocardium cannot function non-oxidatively, so it only functions on oxidative metabolism. So this means the heart cannot incur an oxygen deficit. So the production of ATP in our myocardial cells must match the demand for ATP in myocardial cells. All of these mitochondria would not do much for us in this respect unless we also had a dramatic increase in vascularization. So that ultimately means we have to have a lot of blood vessels, right? Serving blood to the heart to deliver our oxygen, nutrients, to produce ATP and energy and all that good stuff. There is actually one capillary for every myocardial cell, or myocyte. So let's talk about this increased capillary density. Having this increase in capillary density does two things for us. One, it increases our diffusible surface area, and two, it decreases our diffusible distance. So that's important, right? So having a 1-to-1 ratio, meaning we have a lot of vascularization, so one capillary per one myocyte, that's going to increase our diffusible surface area, but decrease the diffusible distance. So the oxygen doesn't have to travel as far. So the distance O2 has to travel is dramatically reduced. So let's talk about the reference person. Reference person has less than one capillary per skeletal muscle cell. The ratio is about 0.75 to 0.85 per one muscle cell. Myocardial cells is 1-to-1. But with training, we can increase our capillary to cell ratio in skeletal muscle tissue. We can go up actually to past 1.1 ratio. We can actually have 1.25 capillaries to one every skeletal muscle cell. So we have a dramatic increase in blood flow and efficiency to our muscle cells, which gives us an advantage for oxygenating cells while exercising. So even though regularly our ratio is about 0.75 to 0.85 per capillary per one muscle cell in skeletal muscle cells, we can get that up past a 1-to-1 ratio and have a dramatic increase in vascularization to 1.25 to 1. Again, this gives us advantage for oxygenating cells while exercising. With cardiac muscle cells, as much as we exercise, we don't increase really the vascularization of our heart. It will always remain that 1-to-1 ratio. Okay, so next we're going to talk about excitation-contraction coupling in cardiac muscle cells, and there are some slight differences compared to skeletal muscle cells. Even though the basic mechanics are the same, there are some anatomical differences that make cardiac muscle cells different. Okay, so here, if we have a diagram of the cardiac muscle cell, this creates a intracellular tubular network. Right? So cardiac muscle cells are set up just like skeletal muscle cells. However, we have the addition of something, axial tubules. Axial tubules. Not only just the transverse T-tubule system, but we're going to add in this horizontal tubule system too. So we have our T-tubules that come down here, like this. But then we also have these axial tubules that run across horizontally as well. Right? So normally in skeletal muscle, the signal has to travel up and down. So when we are having this electrical signal or that action potential comes to the cell, we have to travel up and down the T-tubule system, right? So it's got to go up and down, so forth. In cardiac muscle cells, the axial tubules allows the signal to travel even faster by crossing and not having to go up and down each T-tubule. So not only does the signal can come here and goes up and down, it also goes up and down but across. So that allows the signal to travel with an even greater speed. So if we combine these T-tubules and these axial tubules, you'll have what's called an intracellular tubular network. And we'll continue talking about this setup on the next section.